If we were to rotate this system, drop in some free particles such as these ball bearings, and then view it from the rotating frame, this is what you would see. The particles move in these circular orbits called inertial circles. Now, let's go find out what these are and why they're important. Hi, my name is Ryan. Welcome back to UCLA Spin Lab. In case you missed part 1 to this video, you can check it out right up here. But for now, let's dive a little bit deeper. Newton's second law states that the sum of all forces equals mass times acceleration. Normally, in a rotating system, we'd have Coriolis, centrifugal, and gravity as our forces. But remember that on a paraboloid, at the right speed, centrifugal force and gravity are balanced, leaving us with mass times acceleration equals just the Coriolis force for this system. And with mass canceling on both sides, acceleration equals the Coriolis acceleration. Again, for more information on all of that, check out the Newton's bucket video, which is also linked in the description below. The important part is that Coriolis always acts sideways to the motion. It continuously turns the direction of the velocity, creating circular motion. And for circular motion, the magnitude of the acceleration is related to speed and radius by the following. A equals u squared over r, where r in this case is the radius of the inertial circle. And since the Coriolis acceleration has magnitude a equals 2 omega u, where omega is the angular speed, using both equations gives us u squared over r is approximately 2 omega u, and therefore r is approximately u over 2 omega. So the radius of an inertial circle depends on how fast the particle is moving, though at the beginning we assumed this, which gave us our results, but our system also has some friction, which slows particles down. And a smaller u means a smaller r, meaning that these inertial circles continuously shrink. On a perfect paraboloid, perfect shape, and no friction, you'd have particle motion that looks something like this. Now, accounting for friction, you'd have something that looks like this. But our paraboloid isn't exactly true to shape and has friction, creating these drifting circles, which look something like this. These inertial circles actually bring me to a cool analogy about Newton's first law, which states that any free particle in motion stays in motion. Well, in the rotating frame, any free particle in motion stays in circular motion, because Coriolis is constantly turning its path. That is, of course, all without friction slowing it down. Let's go see all of this in action. Unfortunately for me, a person who's 5'7" and a quarter, can't really see what's going on, so let's move this to the floor and do some experiments. When we enter the rotating frame, the ball moves in these circular paths, which become smaller in radius because the ball is continually slowing down from friction as it rolls along the surface. It follows a path like the one I drew on the whiteboard before. Let's take a closer look, as this is one of the main points of the experiment. In the rotating frame, the particle moves nearly in a circle. As a last trial, we added 2 ball bearings to the paraboloid at different times and with different initial velocities. It just so happens that one stops before the other, but when they collide, energy is imparted to the stationary ball bearing and it immediately goes back into the circular motion, thus showing that free particles moving in a rotating frame travel along circular paths. And now, the big question. Why is this even important? Well, the same Coriolis force responsible for these circular particle motions also influences the motion of air and water on our rotating Earth. From ocean currents to large-scale atmospheric circulation, the same physics we've explored here helps describe how fluids move throughout our planet, and I think that's pretty cool. Roll the credits! Thank you to everybody over here for helping me out with this video. Check out the description below for more information about inertial circles, and I will see you guys in the next video. Take care.